A piston cylinder device contains 0.6 kg of steam at 200 degrees Celsius and 0.5 megapascal. Steam is cooled at constant pressure until one half of the mass condensed. A. Show the process on TV diagrams. Find the final temperatures and determine the volume change. So in this case, I'm going to draw a diagram so that all the information can be clearly shown. So usually I will start with this one is going to be my state 1, and then it's actually going through a cooling process at constant pressure, and then it's going to be state number 2. Given that temperature at the state 1 equals to 200 degrees Celsius, and then pressure at the state 1 equals to 0.5 megapascal. And then because it was a constant pressure, therefore the state 2 here, the pressure P2 is actually going to be 0.5 megapascal. And then this one is actually coming from the textbook from the US, yeah. So they are using one half of the mass is condensed, meaning that half of the mass will be condensed. Condensed means the changes from vapor to liquids. So because here the mass was actually 0.6, and then it is a closed system, therefore the mass in here, the total mass in the state 2 here is going to be 0.6. Its half was condensed, meaning that 0.3 kg will be in the liquid form, and then another 0.3 kg will be in the vapor form. Alright, so now for the state 1 here, temperatures given was 200 degrees Celsius and 0.5 megapascal. 0.5 megapascal was actually equals to 0.5 multiplied by 1000 kilopascal, which is equals to 500 kilopascal. So we have to take a look, yeah, because we have to determine the phase for the state 1. So given that the pressure is 500. So because pressure is given, therefore I have to use table A5 instead of table A4. And then for the 500 kilopascal, the temperatures should be 151. But then, given in the question, temperatures was way higher compared to the 151. Therefore, I can say that state 1 here is going to be superheated region. And then in here, because I have a mixture of liquid and also vapor, therefore the state 2 here is going to be saturated liquid vapor. Alright, so first part of the question asking us to draw a process on a TV diagrams. So I'm going to plot T versus V, which is a specific volume. So usually whenever I draw a TV diagram, I will draw a saturated line, and then the first state here was actually in the superheated region. So most probably my point 1 is going to be somewhere around here in the superheated region, and then the point 2 here, my state 2 is going to be in the saturated liquid vapor region. So this is how my diagram look like, yeah. So yeah, I already done for the first part to construct the TV diagrams. Temperatures, of course, in degrees Celsius, and then V here should be meter power of 3 per kg, and then find the final temperatures. So means that the second part of the question asking for what is my T2, but then I do know that T2 was actually in the saturated liquid vapor. So in here, pressure is the same as the pressure for state 1, which is 0.5 or 500 kilopascal. So for the 500 kilopascal, my temperatures is going to be 151.83. So here is going to be, so my answer for part B is going to be T2 was actually equals to the saturated temperatures at 500 kilopascal, which is equals to 151.83 degrees Celsius. So this one is not that difficult, yeah. And then determine the volume change. So in order for us to determine the volume change, first we need to know, we did know that volume was actually equals to specific volume multiplied by mass. And then for the P, for the state 1 here, pressure of 0.5 and then temperatures of 200. It is in superheated region, therefore I have to use table A6. Pressure equals to 0.5 megapascal. 0.5 megapascal. Yeah, I have to use this area. And then temperatures of 200 degrees Celsius. 200 degrees Celsius, and then I should get the value of specific volume equals to 0.42503. So now state 1, my specific volume equals to 0.42503. 0.42503 meter cubes per kg. And then state 1 should be straightforward, yeah. But then state 2 here, I do know that my V2 was actually equals to Vf plus X VFG for at pressure equals to 0.5 megapascal or 500 kilopascal. So this one can be obtained from the steam table. The only unknown here will be the X. But then I do know that the basic formula for the X or quality X is actually equals to mass of vapor divided by total mass. In this case, mass of vapor for the state 2 here is going to be 0.3 divided by total mass, which is 0.6. Then it's going to be 0.5. Therefore, I can obtain V2 equals to, so I need to find the VF, yeah. VF equals to, for 500 kilopascal, my VF is going to be 0.001093, and then my VG is going to be 0.37483. So now I can use this formula to find what is my specific volume for the state 2, which is in the saturated liquid vapor. So my VF from the steam table, I do know that 0.001093 plus X, which is 0.5, and then as we already used in the previous example, VFG was actually simply equal to VG minus VF. So multiply by 0.37483 minus 0.001093, and then I should get my value of V2 equals to 0.1880 meter cubes per kg. And then the question asking for what is the change in volume. Change in volume is actually equals to volume at the state 2 minus volume at the state 1, and then the volume at the state 2 is just simply equals to mass multiplied by specific volume at the state 2 minus m specific volume at the state 1. But then we can use this one, substitute the value, because the m is actually equal to 0.6, and then just put a value here and here. But then sometimes I can also simplify it something like this, because both sides I got m, therefore I can take out m. So now I have V2 minus V1, mass equals to 0.6 multiplied by V2, which is 0.1880 minus 0.42503, and then I should get the value of negative 0.14222 meter cubes. So negative here means that the volume is actually reduced by 0.14222. So this is what the negative means, yeah. So don't worry much about the negative value here. So now I'm going to move to the question number 2. A piston cylinder device contains 0.05 meter cubes of liquid water and 0.9 meter cube of water vapor in equilibrium at 600 kilopascal. Heat is transferred at constant pressure until the temperatures reach 200 degrees Celsius. So another keyword here, constant pressure process. Therefore, if I'm going to draw my diagram looks something like this. First, I'm going to have state 1, for which in the state 1 here, given that my pressure P1 equals to 600 kilopascal. And then it was heating process at constant pressure. And then because it was at the constant pressure, therefore my state 2 here is going to have the same pressure as state 1, which is 600 kilopascal. But then this time I have temperatures of T2 equals to 200 degrees Celsius, which is given in the question. And then I can also say that state 1 here, it is actually in the saturated liquid vapor. How do I know? Because here, if you notice that they got 0.05 meter cube of liquid and then 0.9 water vapor. Therefore, I should note that this one is a mixture of liquid and also vapor. Therefore, it should be located in the saturated liquid vapor. And then the question asking for what is the initial temperatures of water, meaning that the question asking for what is my T1. And then because it is a T1, so sometimes I can also draw these diagrams, yeah. So my diagram should look something like this. So let's say I want to draw T versus V. So I do know that my state 1, so I just draw a saturation line here. My T1 here was actually located somewhere around here, a mixtures. And then my T2 here, obviously, because at P2 equals to 600 kilopascal, at 600 kilopascal, the temperatures should be 158. But then my temperatures given in the question was 200, which is way above the saturated temperatures. Therefore, most probably it was in the superheated region. So this is my state 1, and then this is my state 2. So by drawing this diagram, obviously my point 1 here, the temperatures for point 1 here was actually saturation temperatures for pressure equals to 600 kilopascal. So I will say that part A, my T1 equals to saturation temperatures at 600 kilopascal, which is equals to going back to the table A5, 600, 158.83. So equals to 158.83 degrees Celsius. So I already answer for the first part. And then second part, determine the total mass of the water. So here the question is actually asking for what is my total mass of the water. The easiest way will be to calculate for the state 1. I do know that specific volume equals to volume divided by mass. And then for liquid, mass of the liquid is going to be volume of the liquid divided by specific volume of the liquid. What is the volume of the liquid? Volume of the liquid is going to be 0.05 meter cubes per. So volume of liquid equal to 0.05 meter cubes. And then what is the specific volume for liquid? This one I can obtain at pressure equals to 600 kilopascal. So going back to this diagram, for 600 kilopascal, my VF equals to 0.001101. So I'm going to write over here, I have 0.001101 meter cubes per kg. So by dividing these two, I should get mass of the liquid is going to be 4.543 kilograms. And then for vapor, I will say that mg is actually equals to Vg, capital V, volume of the vapor divided by specific volume of the vapor. And then Vg here is given equals to 0.9 meter cubes. So 0.9 meter to power of 3 divided by Vg at 600, because it was in the state 1, therefore the value should be 0.31506. So I'm going to put the value over here, 0.31560, which is equals to 2.852 kilograms. So now you would like to calculate total mass. Total mass is actually equals to mass of the liquid plus mass of the vapor, which is 4.543 plus 2.852, and then it's going to be 7.395 kilogram. So yeah, I already answer for the second part. It's not that difficult, but then yeah, I do understand that some students are facing the problem to to differentiate between volume and then meter cubes and then specific volume. Yeah, sometimes I even myself, sometimes I just put it, sometimes we just write something like this. Okay, then we know that this is actually going to be specific volume. Alright, So let me erase this one first. Calculate the final volume. Okay, so for the final volume, here the question is actually what is the final volume. So means that the volume at the state 2, what is the volume here? Okay, first, in order for me to get the volume, I should note that from stream table, I can get specific volume, V2. So V2, because this one, as we discussed before, it was in the superheated region, so I have to use table A6. 600 and 200 degrees Celsius, 600 kilopascal. 600 kilopascal was actually equivalent to 0.6 megapascal, which is this one. And then my temperatures will be 200. Therefore, my specific volume is going to be 0.35, 0.3, is it? I cannot really see. Sorry about that. Confusing. So it's going to be here. So temperatures of 200 is going to be 0.35212. So now I have V2 equals to 0.35212 meter cubes per kg. And then how do I get volume? So usually, let's say I cannot remember what is the formulas, yeah. So the trick here is, what is the unit for volume? So let me erase it first. Okay, so now let's say I cannot remember how do I get the volume here. So actually, by manipulating the unit, so let's say here I want to find what is the formula for volume. Hold on, yeah. The unit for volume here was actually meter to power of 3. And then what I have here is specific volume with the unit of meter cubes per kg. And then you should ask yourself, how do I get meter cubes from this one? How do I get the one? So in order for me to get meter cube from meter cube per kg, I have to actually multiply with the kg, so that I can cancel out the kg. So now I left with the unit of meter cube, which is the same as the left side of me. So means that the specific volume here need to multiply with the mass. So now I will say that volume equals to specific volume multiplied by mass. And then specific volume here was actually equals to 0.35212. And then how about the mass? If you, I already erased it. If you notice that the mass was actually already being calculated from part B above. So I have to multiply with the mass which I get from the part B above, 7.395. So now I'm going to get the volume equals to 2.604 meter to power of 3. So this one is not that difficult, yeah. And then last part will be show the process on the PV diagram. Before this, what I show you here is a TV diagram, which is quite easy for us to see because of pressure is constant. But then if they ask me to draw PV diagram, so I'm going to plot, this is my saturated line. So this is going to be my state 1. And then here is going to be my state 2. Why? Because the pressure is constant from the state 1 to the state 2. So the diagram look is not going to be look as nice as TV diagram, but still we can plot whatever given, either PV or TV diagram, as long as you understand that, okay, this process is constant, therefore state 1 and state 2 should be a straight line. Alright, let's take a look at the last part of the questions, yeah. Alright, a piston cylinder device initially contained 50 liters of water at 400 degrees Celsius and 200 kilopascal. Heat is transferred to the water at constant pressure until entire liquid is vaporized. What is the mass of water? Um, Alright. Let me think first. So, even that. Okay, I already got it. So, this one, first, I have a state 1. And then I'm going to have state number 2. State number 2 here, I will say that until entire liquid is vaporized. So it's going to be saturated vapor here. And then here is going to be saturated liquid. And then we have temperatures of 40 degrees Celsius. Sorry about that, spelling typo error. And then T1 equals to 40, and then P1 is going to be 200 kilopascal. And then heat is transferred. So this is a process, heat being transferred, so that my thermodynamic system was changed from state 1 to the state 2, but then it occurred at the constant pressure. Therefore, I can say that pressure at the point 2 here is going to be 200 kilopascal. And then the question asking for, what is the mass of water? So I can say that state 1 here, I have saturated liquid. So V specific volume for the state 1 here is going to be specific volume of liquid at 40 degrees Celsius. Then it's going to be 0.001008 meter cubes per kg. And then I do know that because this one they give me the volume in the unit of liter, therefore I have to convert. 50 liter is actually equals to hold on, 1 liter equals to 10 to power of negative 3 meter cubes. So this one is going to be 50 multiplied by 10 to power of negative 3, which is equals to 0.05 meter cube. Supposedly they give me a table with the unit conversions. Let's say you cannot remember how to convert from liter to meter cube, you can just simply ask me even during the finals, because this one should be given, because we don't have to remember that liter to meter cube and etc. So this one I just, because I'm dealing with the unit conversion a lot, therefore I do remember that 1 liter equals to 10 to the power of negative 3 meter to the power of 3. So when I convert it, I'm going to get the volume of 0.05 meter cube. So in order for me to calculate the mass at the state 1 equals to specific volume equals to volume divided by mass equals to volume divided by specific volume. So now I have volume 0.05 divided by specific volume for the state 1. Then I'm going to get the mass of 49.61 kg. So now I ready to solve for the first part of the question, which is what is the mass of water? What is the final temperatures? Because it was located at the saturated vapor, therefore I do know that my T2 is going to be T saturated at 200 kilopascal. Then I'm going to get the value of 200 kilopascal pressure. So my T is going to be 120.21. So 120.21 degrees Celsius. That one should be quite easy, yeah. Determine the total enthalpy change. Total enthalpy change meaning that what is the H2 minus H1. But then I do know that from steam table, I can get H2 minus H1. And then here, I can get, to get the H here, H2 was actually equal to M multiplied by H2. Why? Because H2, the unit for H2 here is actually kilojoule per kg. And then if I multiply by the mass, which is kg, then I'm going to end up with the kilojoule, which is correct because represented by the capital H. Let me erase it because this question sometimes can be a little bit complicated. Yeah. Alright. Alright. So to calculate the enthalpy, I will say that, oops, sorry about that. Let me erase first. So I will say that first I need to calculate for the H2 minus H1. H2 here is for the Hg at 200 kilopascal minus HF at, it's just the same, yeah. So here I'm going to say that 40 degrees Celsius. So Hg, because it was saturated vapor for 200 kilopascal, therefore is going to be 200, and then I need to find the Hg enthalpy. Yeah, see, we can read from here. So the enthalpy should be 0.2706 at 2706.3. So it's going to be 2706.3 minus HF, which is at the 40 degrees Celsius. So my HF is going to be enthalpy 167.53. See, because initial condition, because as I said before, for the state 1 here, if you remember that it was a saturated liquid. So I will say that this one is going to be 167.53. Therefore, I'm going to get the value of H2 minus H1 is going to be something kilojoule per kg. So if I want to calculate for the total enthalpy change, which is H equals to mass multiplied by H2 minus H1, and then I'm going to get the mass given equals to, no, the mass already calculated for the part A. So it's going to be 49.61 multiplied by 2706.3 minus 167.53, and then I'm going to get the value of H equals to 125.95 kilojoules, because H should be unit of kilojoule, but then if the specific enthalpy is going to be kilojoule per kg. And then the question asking me to draw a TV diagram. So my TV diagrams, so T versus V, temperatures with the unit of degree Celsius, V the unit of meter cubes per kg. Most probably my state 1 should be somewhere around here, and then my state 2 will be somewhere around here. Sometimes you will notice that in the textbook they are saying that actually the state 1 should be somewhere around here, but then you should also note that point 1 here and point 1 here is not much different. Sometimes I can just simply assume that the value, the properties here is actually just the same as properties here, because the value are the difference in the value are very small. So I hope that the question which you already discussed here will help you to have a better understanding on how to apply the STEAM table. If you notice that there's a lot of different scenario, because if you remember that sometimes let's take a look at the TV diagram, yeah. So let's say this is my TV diagram, and then I have saturated line, and then if you remember that sometimes the question can start from here and then end up here, and also sometimes we can also have the question starting from here and then end up somewhere around here. So this one is going to be state 2, and then this one is going to be state 1. Sometimes also we can have a process, meaning that the change of the from here and then end up here, and etc. There's a lot of scenario, and then if I'm going to cover for every single process, and then it's going to be a lot of questions. But then you can also try couple of questions from our textbooks. Thank you.